Hi guys, okay, so we're looking at chapter 10 continued and we're actually on 10.7 now. So we wrapped up Lewis structures last week. We'll spend a little bit more time in class with those, but now we're going to move on to shapes and geometry. So this is 10.7 and it's going to look at molecular and electron geometry as well as the VSEPR theory. So 10.7 is predicting the shapes of molecules. Oh, actually, let me pause really quick. If you don't have a piece of paper out, now would be a great time to get a piece of paper out because we are going to have some U-tries in this video. So you'll also have to submit those U-tries to your Canvas page, so make sure you have that piece of paper out and you're ready to go. And you're ready to pause when you get to a U-try. So pause, get your paper out. All right, let's get going. So 10.7, predicting the shapes of molecules. So really what we're going to be looking at here is we're taking what we learned last week, those Lewis structures. Remember, Lewis structures are those dot diagrams. Remember, we have that central atom, whatever we're looking at, and there are valence electrons that we put around that central atom. That tells us how many valence electrons that atom has, and we can also do Lewis structures for ionic and covalent bonds, and we can look at how things are bonded together and how their valence electrons are shared. So basically what we're going to be doing in this unit is taking those 2D Lewis structures and then looking at and using that 2D Lewis structure to determine what it would look like in 3 dimensions, because again, these bonds and these atoms aren't two-dimensional things. They make up all things around us, right? They make up tables, they make up chairs, they make up of everything, right? So those things are all three-dimensional things. So these atoms must also be three-dimensional as well. And so predicting what their shapes and what the shapes of these molecules look like, that's what we're talking about. And so it's it's using Lewis structures to predict what these 3D shapes will look like based on how many electron groups it has. So these electron groups are what we're going to sort of determine what they are. What are electron groups and how does that predict shape? So that's what we're looking at. Another term you might hear for electron groups, and let me get a pen going here, are things called domains. So electron groups can also be called domains. And in fact, on your homework assignment, it's going to reference what domains are on the POGL. Domains are the same thing as electron groups. And I'll keep referencing back to this, but by the time you do the homework assignment, you should understand that those terms are synonymous with each other. Okay, and then the last thing on here is the VSEPR theory. So the VSEPR theory is that essentially it basically says that all these groups, these electron groups that are around these atoms, want to repel each other. They want to be as far away as possible from each other. They don't want to be anywhere near each other. So we'll sort of look at the practical application of what that means. Okay, the next thing we have to understand is electron geometry versus molecular geometry. So most of the time, what they're going to ask you for is this molecular geometry. So it's what is this shape look like in 3 dimensions? What does this Lewis structure look like in 3 dimensions? And you're going to be predicting this molecular geometry. And that's just the arrangement of the atoms in nature in 3D. The electron geometry is looking at how the electron groups or those domains are arranged. And this will make a little bit more sense as we go through some examples. But these are 2 different things. And the one that you are more likely to have to explain is molecular geometry. We might come back to this page. Okay. And the next thing, so VSEPR theory continued. So electrons want to be as far away as possible from each other. That's the repulsion part of VSEPR, the R. So they're going to orient themselves in such a way that they are as far away as possible from each other. And there's 5 geometries we're really going to be focusing on in this class: linear, bent, trigonal planar, tetrahedral, and trigonal pyramidal. So what I'm going to do right now is go through all 5 of these examples and show you what they look like and how to draw them and sort of what that means. Okay. So let's start with the first one, linear. So if something has a molecular geometry, so right now we're looking just at the molecular geometry. So remember, we have electron geometry and molecular geometry. Right now we're looking at the molecular geometry. Oh, this doesn't want to work as well up here. Geez. So right now we're looking at the molecular geometry. And So if something is linear, that means that the way that the atoms are arranged in nature in its three-dimensional shape means that it's in a line. Now, if something's linear, it also means that there are two things around the central atom. So in this case, we're looking at CO2. So in order for me to determine what the molecular geometry is, I first have to draw the Lewis structure. So step one is draw the Lewis structure. So I have CO2, and if I were to draw this Lewis structure, it would look something like this. Now, in order to know how to do this, you'd have to go back to what we learned last week. How many valence electrons does carbon have? How many valence electrons does oxygen have? Determine the total number of valence electrons, and then draw your Lewis structure. So we kind of bypassed all those steps, but just note you do have to do that in order to get to this Lewis structure. So we're not throwing away what we learned last week. So now we have our Lewis structure, and we need to predict what it's going to look like as a shape. What is its shape going to be? In this case, we have two things around our central atom. So in this case, carbon is our central atom, and we have two oxygens on either side of it. Those two oxygens on either side of it are giving us a straight line shape. So there's nothing causing them to be closer or anything because of this VSEPR theory. They want to be as far away as possible from each other, and that would make them about 180 degrees apart. So when you see CO2, you know that its molecular geometry is linear and that those molecules are going to be approximately 180 degrees apart. And you would call this linear. Now, here are the two electron groups. Remember we said there are things, I have two things written, or two electron groups, or I mentioned on the other side it can be domain. So in this case, these are the two domains. There are two things on either side of the central atom. When there are two things on either side of the central atom, that gives you a linear shape, okay? And they also, again, want to be as far away as possible from each other, so it's going to have that 180 degree angle. That's as far away as they can get from each other, okay? So that's linear. Now this next one we're going to look at is trigonal planar. Now trigonal, or tri, you should think of three, and plane means they're all existing on the same plane. So if it's trigonal, anything, that means there are three things around the central atom. On the last side, we said there are two things around the central atom. On this one, there are three things around the central atom. So what we have here is, for our example, is H2CO. Now, in this case, carbon is our central atom, and we have two H's on either side and our O, and everything has an octet. Carbon has 1, 2, 3, 4. Oxygen is 1, 2, 3, 4, and hydrogens are okay with their duet. So this is our Lewis structure, and we can identify how many things are around the central atom. 1, 2, 3 things around the central atom. So the three things that are around the central atom are, and let me see if I can grab a highlighter here. Looks like I can't. Okay, so the three things that are around are this hydrogen, this oxygen, and this hydrogen, okay? So if we were to draw this three-dimensional shape here, we would draw it like this, right? We'd have our carbon in the middle, and then these three entities, or these three things around our carbon. Now again, the VSEPR theory says these things want to be as far away as possible from each other. So they're going to be always about 120 degrees apart from each other. Now this is sort of hard to tell in this diagram, right? Like this angle technically looks larger than this angle, maybe if I'm visually looking at it. But in nature, the way that this would be displayed is exactly, or approximately, 120 degrees in between. Now, remember earlier I mentioned there's molecular geometry versus electron geometry. We're still talking about molecular geometry. So trigonal planar is the molecular geometry of this. Okay, next one, tetrahedral. Tetra means four. If you didn't know that, tetra means four. So in this case, that means there are four things surrounding the central atom. So in this case, our example is CH4, so we have carbon and 4 hydrogens around our 1 carbon. Again, this is the Lewis structure for that. Now, if we were to draw this out, we'd have our 1 central carbon atom and our 4 hydrogens surrounding it. And the angle that exists between these 4 hydrogens is 109.5 degrees. So again, in this image, it's hard to tell. These apparently look closer than this one. but you would know that 109.5 degrees is the approximate angle between each of these. And again, this is the maximum distance each of these can be to be as far away as possible from each other. Again, maintaining that VSEPR theory. Okay, and again, this is still the molecular geometry. That's still what we're looking at here. Let me write it down here. Molecular geometry. Not sure what's going on with this pen here. Okay. It's having a hard time today. Okay. All right. Now, the next one is trigonal pyramidal. So you'll notice here, trigonal means there are 3 things around it. But what's interesting here is this one, our NH3, actually has 4 things around it. And let me explain where those 4 things are. So if I were to draw the Lewis structure for NH3, I've got nitrogen, my 1, 2, 3 hydrogens around it. So we would say that there are 3 things, but there's actually a lone pair here. And a lone pair counts as an electron group. It counts as something that is around our compound here. So we actually have to say there are 4 things surrounding this. And now this is when we're going to talk about the difference between electron geometry and molecular geometry. So for electron geometry, I would say that there are 4 things surrounding it, 1, 2, 3, 4, and that is tetrahedral. Now, this is also going to have the same molecular geometry. For molecular geometry, it's going to have a different electron geometry. So this one says that it's tetrahedral because there are 4 things surrounding it, 1, 2, 3, 4, but the actual shape is going to be trigonal pyramidal. It'll be different. So here's our central atom. Here's our 3 hydrogens. Those are going to be about 106.5 degrees apart. And our lone pair is going to act slightly different when we're looking at a molecular geometry. It's going to give it sort of this it'll exist sort of. So even though there are 4 things around this compound, we're actually going to end up more similarly with a shape like this. So our electron geometry and our molecular geometry are different. The electron geometry says there are 4 groups, making it tetrahedral. But the molecular geometry says there are actually only 3 groups around it, making it trigonal pyramidal. So that's something that you have to be aware of, and we'll do an example of that together. Okay, and I think this might be our last example, bent. So we'll look at water. Water, if we were to draw the Lewis structure for it, has 1 central atom, that's oxygen, and then 2 hydrogens coming off of it. But there are 2 lone pairs on top of our oxygen. So if I were to count how many things are around my oxygen, my 1 central atom, I have 1, 2, 3, 4 things around my central atom, making it tetrahedral in shape. But when I actually go to draw this out, the 3D model, I really only have these 2 things on it, my 2 hydrogens, with 2 lone pairs attached to the top. So what I actually get is this bent shape, and it looks just like this. Or I'll draw it like this, just like this. It's like linear, similar, where there's only 2 points, but it has a bent shape. And the reason it actually has this bent shape is because of these lone pairs. The hydrogens want to get far away from these lone pairs, so it's actually going to push them or repulse them to be further away from these 2 lone pairs. So that's actually these 2 lone pairs up here would give it this bent shape. So it looks linear, but you actually wouldn't call this linear at all. You'd say it has an electron geometry of tetrahedral because there are 4 things around the central atom, but it has a molecular geometry of bent. So those are the 4 things. Now, here are the 5 things, I'm sorry. So let me show you this. This is a summary chart. So if it has 2 electron groups, 2 things bonded to it, but no lone pairs, it's linear. And the bond angles that exist in between are 180 degrees, and you're going to end up with something approximately with this shape, right? And you can go through and do this for all of them. And it gives you pretty much an example. If it has 3 electron groups coming off of it, but only 2 of them are bonded and 1's a lone pair, then you've got something like trigonal planar and a bent shape, right? So you can go through and use this as a reference chart, although I think it's slightly easier to just be able to identify them based on sort of what they look like as you draw them out. Okay, so we're going to do a you try. So this is actually going to be where you pause, complete these, and then the answers are actually going to be on the next slide. So go ahead and pause here and do your you try. Okay, so here is PCl3. So I'll go ahead and draw out all the whole Lewis structure with you. So P has 5 valence electrons, chlorine has 7 valence electrons, but there are 3 of them, giving us 21 valence electrons, plus those 5 from our phosphorus gives us a total of 26 valence electrons. Now, if I were to draw the Lewis structure out for this, I've got my P in the middle as my central atom, and my 3 chlorines surrounding it, and I have all of them having an octet with one lone pair. So if I were going to talk about the electron geometry for this, I would say there are 1, 2, 3, 4 things surrounding my central atom. So the electron geometry says that it's tetrahedral. There are 4 things around my central atom. But if I were to draw this, I would have 1, 2, 3 things around my central atom with one lone pair, and it actually makes this trigonal pyramidal. And it gives it sort of this shape, which we saw on the other page. Okay? And then the bond angle that's going to exist between each of these is going to be 109.5. Okay? And then, and then for this one, the ClNO, and I think on that last slide, it said that the N is the central atom. So we drew our Lewis structure with N as the central atom, and our oxygen and our chlorine on either side. There's one double bond and then a lone pair on the nitrogen. That's the correct way to draw this. So what we would say is there are 1, 2, 3 things coming off of this. There are 2 bonding groups, 1, 2, and there is 1 lone pair. So if we were to draw this out, the molecular geometry would actually be bent because we'd have our oxygen and our chlorine and our 1 lone pair pushing down on these 2, and we really only have 2 bonding groups at this point. We only have 2 bonding groups at this point. So this is going to give us our bent shape. 2 bonding groups here and here. So our shape is bent. Okay, so if this is confusing to you, this is actually the last slide. Please reach out to me, rewatch this video, look at your textbook, and also do the homework assignment because it will walk you through some of this, okay? All right, have a great day, guys.